Madari.
Yes, brother, we can hear you.
Okay, should we start?
Yes, brother, we'll start.
So, concrete part, concrete part. Concrete part, we have two major portions. First one is design of residential, and the second one is a commercial building. Okay. We have done almost all things regarding. Nothing is left. And in commercial part, we have only done a bit about earthquake loading and developing the structural scheme. This smaller part, the residential part is larger part. So for residential part, first of all, what we have to do in the first step we have to carry out after on this architectural plan. The paper this architectural plan would be given. First thing we have to do, develop its structural scheme. We have to draw its structural scheme plan given. Afterwards, we have to draw framing plan. In framing plan, we have to draw beam layout plan and lintel layout plan. We have to show where we are going to provide where we are going to provide beams, where lintels are to be provided. And afterwards, drawing these two framing plans, we have to design these. Design beam and design lintel. These portions we have to do. We have to show this. And apart from this, if we go to this paper, we directly go to the papers. First question is, you have to design a residential building. What types of structural drawings would be required? That what structural drawing we would be needing for residential building. For that, first we require a structural scheme. Then we require a beam layout plan, a lintel layout plan. These three things. And from design, we can show the beam section as well as column section. Oh, sorry, lintel section. So these section would get after designing these parts, beam and lintels. Third drawing would be our the sectional drawings, beam sections as well as. Apart from these, there are also some other drawings which we can find out from. This is from CECG, Construction Graphics sector, and the structural drawings are given are these. That we have to draw foundation plan as well as excavation plan. These are the same things. Excavation plan is for the excavation, while foundation plan, in foundation plan we show the foundation sections. Like wall section is like this and column section. So section foundation plan we show the section. Excavation plan we show how the excavation will be carried out. Enforcement details of slab enforcement details, plumbing works, indoor doors and windows, and electrification, bathroom and kitchen details. So all these are structural drawings. And one thing extra is specifications. We have to show by which code we have carried out this design and general notes. General notes regarding this. So these are all drawings. You have to memorize them. That they are simply asked what type of drawing should be asked, should we draw. So the first is structural scheme, then framing and design, and then there are foundation plan, enforcement, plumbing, windows, electrification, and bathroom and kitchen details. So we have to write all this in this first question. This is of 6 marks. We have to write all this. Second question is save software. We have not done this up till now. We will do this in the final. So if we move to the second paper, in this they are saying that sketch the structural scheme. So the first part our work was we have to draw the structural scheme. Residential portion, the first part is we are going to draw a structural scheme. So if if this ground floor and first floor plans are given. For structure scheme, we have to first draw its outline. The outline is almost like this. So first we have to draw its outline. Thing like this. Thing like this. So first we have drawn the outline. Then we have to show the walls in the drawing by dotted lines. So this is for bathroom, the bedroom and kitchen. This is for kitchen. This is for bedroom and the stairs and living room. So this whole slab is for living room and this one is for stairs. So now we have shown the slabs in this slabs and walls, the structural scheme. Third thing is we have to show the beams. We have shown the slab panels. We have to show the beams. So where the beams would be required. Firstly, the beam would be required if there is if there is 4.5 inches wall on floor on ground floor. Suppose we are drawing the structural scheme of ground floor. So if there is 4.5 inches on wall, 4.5 inches wall on ground floor, then a beam must be required above it. We must draw a beam above it. So if there is a 4.5 inch wall, so we can see this wall is clearly a 4.5 inches wall. So we will be requiring one beam here. We can name this as B1, like this. That beam over 4.5 inches wall. Second, is there any other 4.5 inches wall here? This one. This stair. So this wall is 4.5 inches, so we require a beam here also. In the middle of the stairs. So second beam would be required here. So first is the first beam we have to draw wherever there is 4.5 inches wall in the ground floor. Second thing is we have to draw a beam if there is 9 inches wall on first floor. If the first floor contains a 9 inches wall and there is no wall below, that if the first floor has a 9 inches wall but there is no wall underneath it, so we have to draw beam for that. So for example, look at this. This shows the bathroom and this is the kitchen portion for first floor. And if we superimpose this first floor plan on the ground floor plan, you will see this portion, these walls, these two small walls, they will lie something like here. So these are 9 inches walls and there is no wall underneath them. So we require a beam here in the ground floor to support these walls. So the beam B2 would be required here to support this. And how can we know that this is in the center and not on the edges? Because if you see, this is the terrace portion. They have written this is the terrace portion. So the terrace portion, so the the roof ceiling of ground floor is the ground level for the first floor. So for example, this is the terrace. So this terrace must lie on some ground floor slabs. Then so this would be lying almost here. So this terrace cannot come here because this is an open space. Of course, this terrace would be lying somewhere on the slab of ground floor. So this terrace would be here. So we can know that these walls, these two walls would lie somewhere in between the living room. So a second beam would be required here. This B2 beam. So we can say that if there is no 9 inches wall on first floor, we have, if there is 9 inches wall on first floor and there is no wall on the ground floor, then we require some beam there. Third thing is, if we have a staircase like this is our staircase. We have to cut the slab here, because if we do not cut this, we cannot go to the first floor. So we have to cut our slab in case of stair voids. So first, if we cut the slab, if I draw it like from here, this is the wall of ground floor, and this is our staircase. This is our staircase. We have to go up from this direction. So if we have to cut, so this is stairs are like this, and from here like this, top. So if there is slab on top of this portion, we cannot go to the first floor. So we have to cut a portion from this slab. We can cut it partially like this, that we only cut this half portion. We only cut the top portion of stairs, or we can cut it by whole, like this one. We can cut it whole. Any option can be adopted. So in this case, if I move the previous beam, this portion we can either this portion we can either remove it or we can retain it. That's no issue. But the bottom portion, this must be removed because we have to move to the first floor. So either we can provide an open void like this, like this cross shows open void, or we can provide a whole void for stairs like this. This one. We remove the whole slab of stairs. So this the whole slab, if we remove, this is more easy for us, because if we remove the whole slab, only a beam would be provided here. We will require only a beam here. But if we remove the half portion like this one, we would be requiring a beam here, a beam here, and a beam here, like this. So it is easier if we remove this whole stair void like this and simply provide one beam here. Are you getting my point that how we have to remove the staircase slab? So this third beam, this would be provided in case of stairs. In case there are stairs, we require a beam at the edges because we have to cut the slab. So the unspotted portion should be spotted somewhere. So we are providing a beam here. All right. And the fourth beam, this would be provided if there is a depressed slab. If there is a depressed slab, and where do we provide depressed slab? If suppose this is a ground floor washroom, and on top of this, if there was another washroom in the first floor. Remember, if there's a washroom on top of washroom, then we are only going to provide a depressed slab. That if this is a washroom, and here it's also a washroom. In this case, there is no washroom. But if suppose there was a washroom, then we are going to provide a depressed slab. Why? Because this washroom plumbing, this must be fit in below the ground floor level. So this is a room level. This is the room level of first floor. If I say that this is a room level of first floor, the slab of washroom of first floor should be like this. It should be below the first floor slab. This was the slab. This should be the finished floor level of washroom. This is finished floor level of room. So the finished floor level of washroom must be below the finished floor level of room. Why? Because this portion is used for plumbing. We install pipes and everything extra. So this is why we provide a depressed beam here. This portion, this is known as a depressed beam. This connects both the slab of the room and the slab of the washroom. So if there was a washroom on top of a washroom, so we are going to provide a depressed slab there. So for depressed slab, we require this depressed beam, TB. In this case, there is no requirement because there is no washroom on the first floor. But if in the paper a washroom comes on top, then we require a depressed beam here. We're requiring a depressed beam here and here in both sides to support the slab. Okay. So this is why these are four major cases why we require a beam. The fifth one can be that if the slab of ground floor is very large. For example, if we look at this living room, this one, this slab is like 10.5 and 16.75. For example, it was 26.75 instead of 16.75. Then we cannot provide this large slab in one go. We have to divide this into two parts or more parts, like we are providing a beam here. In this case, naturally, from due to this walls, we are going to divide this slab. But even if there were no walls on top of this, we would have to require a beam here because we cannot provide a very large slab that would require too much depth. So we must have the constant depth of slab in all the rooms of the house. Okay, so the structure scheme would be like this. Then B1 we would be requiring here like this. B2 due to these walls here. B2 like this here, and B3 we are showing this whole stair void here. So B3 would be like this. Okay, only three beams are required. Any issue in this?
No, brother, everything clear.
Okay, so this is a structure scheme. We have shown the slab panels. These are the slab panels. We have to show the beam. This is our B1. Just clearly show it. This is almost our B2. And this is like our B3. So we have to show it clearly. Just I'm sketching it roughly. So we have shown the slab panels. We have shown the beams and voids. So our stair void is just like this. This is our stair void. So we will show our stair void by a cross. And if there was a depressed portion, we have to show it by dotted cross, like this one. If there was a depressed slab, but since there is no depressed slab, we have. So this is how we have to draw the structure scheme of the given plan. After the structure scheme, we have to draw the free body diagrams of beam. We have to draw the free body diagrams of beam. So we have three beams, B1, B2, and B3. We have to show their free body diagrams. So if we see this B1, this B1 is lying on wall here and on the wall on both sides. So B1 is supported by walls on both sides. So it would be a simply supported beam like this one, and a slab load would be coming like this. The UDL load would be acting on beam and due to the slab. So B1 would simply be a simply supported beam. And its section, we can provide it like this. This is slab and this is drop. So we can simply provide a drop beam in this case because there is a wall underneath it, and this wall would hide our beam. So we do not need to do any extra thing, just simply provide a drop beam. So this would be section of beam and this would be our free body diagram. And this is section. Okay. So for our B2, if you see our B2 is present in the middle of the room. This room, this living room, B2 is in the middle of the room. So we cannot provide a drop beam here because if a beam is hanging in the middle of room, it would be looking very bad. Uh, this will destroy our aesthetics. So for B2, we have to go towards concealed beam, CB. We can write it as CB2. We would be providing a concealed beam here. So its end condition are again the same. It's not lying on anything, so it would be like this, simply spotted. But its sectional drawing would be different because it's a concealed beam. So concealed beam is upturned is on the towards the top. This is the slab thickness, and this is maximum of 75 millimeters. We can provide more upturning than 75 because if you provide more, then the floor level of the first floor would rise on that location. So that would hinder our movements. So we cannot provide it more than 75 millimeter. And why 75 we are using? Because if you remember, if we lay out a slab, this is a slab. On top of slab, we provide 75 millimeter brick ballast. So we are removing the brick ballast here and simply provided the beam here. And on top of that, we require 60 floor finish. It would be a PCC or something. So this is concealed beam, and we are only going to provide it maximum of 75 millimeters plus slab thickness on the top. Okay, and B3 this one. So B3 is we can in the front of stairs we can simply provide normal drop beam. No need to go for concealed beam here. We can simply provide a drop beam here. And again, it's lying on two walls. So this it's a simply spotted beam, and simply we can go for drop beam. Okay, so this is how we are going to show the beams section as well as their free body diagrams. For example, if a beam was lying on a column, if there was a porch, we have a porch like this, and there's two columns, and a beam is lying on top of them. And in this case, the free body diagram of the beam would be something like this. There are two fixed supports on each side, and UDL is acting on this. Because we provide the column steel into we anchor the column steel into the beam steel. So movements will be transferred from beam to column, and the support would be our fixed support. These movements would finally be transferred to the columns. Okay, so this is how we have to draw the free body diagrams of the beam. So our second part show the free body diagrams. The third part is design the slab panel of living room and sketch the reinforcement details. So we have to know two things for designing. We have to know the design of simply supported beams and design of two-way slab by ACI coefficient methods. ACI coefficient method. So the design of simply supported beam is very easy. Only the difficult thing is how to calculate the loads. For example, if there's a slab like this one is a slab, this is a slab, and I think this one is also a slab. So these are tools we have to design this beam. Okay, that we have to design this one beam. So it has two slabs on the top portion and one slab on the bottom portion. So we can see this slab, the bottom one slab. This is clearly one-way slab. I'm showing it by one. Why? Because it's length over span ratio, length Lx over Ly ratio. Lx is the shorter dimension always, and Ly is the longer dimensions. Ly is the longer dimension and Lx is the shorter dimension. So Lx over Ly ratio, it's less than 0.5. You can clearly see that its Lx and Ly ratio is less than 0.5. So it is one-way slab. One-way slab. So for one-way slab, we know that half of the load, we can simply divide it into two parts. So this half load, this one, would be transferred to beam here. Okay, that half of the load from the one-way slab would be transferred in this direction and the half in this direction. So we are not concerned with about this one. So for our beam, the half portion of this one-way slab would contribute. Similarly, for the top, for example, this is also a one-way slab. This one is also one-way slab. So you can simply divide this is Lx, smaller dimension is always Lx, larger is Ly. Simply divide it into two parts, and the half load from this portion would be transferred on beam here. And finally, for this is two-way slab. You can see this, we can check it by Lx over Ly ratio. So for example, this is a two-way slab. And this is shorter dimension, so this is Lx. This is larger dimension, so this is Ly. Lx and Ly of each slab would be different depending on their shorter and longer dimensions. And there are clear distances between the sports. So this is Lx and Ly of this beam. So we have to remember that for a two-way slab, the load distribution would always be like this. For smaller sites, it would have triangular load distribution like this. And for the larger side, it would have trapezium. So the trapezium load would go on larger sites Ly, and the triangular load would go on this shorter side Lx. Okay, so for this beam, you would have this triangular load, shown in green. So we can simply calculate its area. So we have three different loads on this beam. This one-way load, this one-way load, and this triangular load. So we can simply calculate these areas, the areas of this load. The area, we can say this is load A, this is load B, and this is load C. So what we have to do, we have to calculate the area of A portion, B portion, and C portion. A would be simply Lx by 2. Sorry, was there any connectivity issue? So for A portion, simply our area would be Lx by 2. This is Lx. So Lx by 2 into Ly. This one is Ly. Simply we can calculate the area as Lx by 2 times Ly. Okay. And for this B portion, again the same Lx by 2 into Ly. Lx by 2 into Ly. And for the C portion, we can calculate this triangular area. This will be half into base into height. So 1 by 2 base is Lx, height is also Lx. Why? Because we are assuming this as a triangular load. This is at 45 degrees. So it would have same dimensions. We are assuming this angle at 45 degrees. So if this was Lx by 2, this one would also be Lx by 2. Sorry, this is Lx by. Okay. So this is how we can calculate the areas. And we can simply multiply the area with the length of the beam to get the UDL on the beam. Any issue in this? Simply add these areas and multiply by length and get the UDL on the beam. After getting the UDL, we can find the bending moment as omega squared by 8 because it's a simply supported beam. And from bending moment, we can find rho is equal to mu over bd squared. And omega is equal to rho is equal to omega 1 minus under root 2.614 r over f3 dash. So we can simply use this formula to calculate rho, and AS is equal to rho BD. So we can find the area of steel required for beam like this. So simply put beam, the only difficult thing is this calculation of area. Any issue in this portion? That how we have to calculate the area of the load contributing load tributary area. It should be moved to the slab portion.
Brother, I have one question. While we are
Yes.
drawing the beams and while we are designing the beams, if one beam is resting on another beam, means like
Yes.
at that times how we can take that middle load?
Okay. Okay. So for example, this is okay. This one was our these one are slab
Like
portion.
yeah,
And for example,
we can use
if
it.
we require a beam here like this, but also yes, sorry,
Yes, brother, this thing.
this thing that we are requiring this long beam and this short beam. So either there are two ways to do this. That either for the green portion, this is the for the green beam. We can either design it as a simply supported beam, the green one is a simply supported beam, and its reaction would act as a point load on this blue beam. So the blue beam would be like this. So at the center of the blue beam, almost center, the reaction from the green beam, this reaction would act as a point load on the blue beam. So this is our first how we can design this as these two beams. The second case would be we design this beam first. For example, we design this blue beam first. So this is the blue beam. This is suppose we are showing that this beam is on the top and the green beam is at its bottom like this one. So the load which was present here at this portion this would act as a support here. So the blue beam would become a continuous beam that it would have three different supports. One support this wall resting, the second support this middle portion, and the third support another wall. So it would become a continuous beam. And what direction would we get from this portion? We would be applying this section at this beam. So we can either design the place the second beam at the top, the blue beam at the top, and design it as a continuous beam, or we can place a green beam at the top and designs both beams as simply supported beams. The better option is to have the longer length at the bottom. That this beam, if we do this, if we have this at the bottom, so we have to do design both of them as simply supported. So that would be more easier for us. Otherwise, continuous beam would have a larger. We have to do indeterminate analysis for this beam. So it would be a longer procedure. Okay.
Okay,
So
brother.
this was for beams. The second is for slab. For, only one method has been taught to us in this portion. So that is ACI moment coefficients. So its procedure is simple. That, for example, if we have a slab panel like this, the longer dimension is Ly, the shorter is Lx always. We have to find M, that is the ratio of Lx over Ly, and we have to check the case of the slab. For example, it has continuous in this direction and it is continuous in this direction. So we can check its case from the tables given in the book as well as the manual. So for example, if its case was 4, we just have to check its case. So we know the M, we know its case. We can find its thickness as if I open the book. Yes. So the cases are given here. This one case. This the solid line shows that this is simply supported on all sides, and the hashed line shows that it is continuous in on that side. The case 3 means that the smaller side is continuous. That means Lx side is continuous, Ly side is simply supported. In this way, we can find out the case of our slab. So from the case of the slab, we can use this formula for thickness. This is the formula for the depth of or thickness of the slab. So ln is always the clear span in shorter direction. That means Lx. So m is the value we just calculated now. So we can use this formula to find the h, and we know that d in short direction would be h minus 27. D in long direction would be h minus 36. Here just to memorize this. That means that in x direction, for example, this was slab, and this is Lx. This is Lx. In x direction, the steel lid would be at like this. This would be h minus 27. That from the top of the slab, the depth to the center of the bar would be h minus 27. Why? Because we provide 20 cover here for steel, and we assume that the bar is 13 millimeters, so approximately 7 millimeters. It's towards the center. So this is for the shorter direction. For longer direction, we place steel above the shorter direction like this. So its effective depth would be reduced, so it would be like P minus 36. Okay, so in shorter direction, we provide this bottom steel, and in longer direction, we provide bottom steel on top of the shorter steel. Okay, so if we go through here, we find there are many panels in paper. Only one panel would be given. So we have to calculate H minimum for one panel, and D in short direction, D in longer direction. We calculated. Then we calculate the loads exactly like beam. That for our RCC slab, whatever the thickness was, 8 times 2400, and brick palace 75 millimeter, and floor finish of 60 millimeter. So we add them. This is dead load, live load. We assume 200 for residential building. We can also assume 250 for residential and 300 to 350 for office or commercial buildings. Factored live load we calculated. Yes, minimum is 0.22 BH. For grade, this is for grade 300 or 280 megapascal. If it was 420, we use 0.0018. This option would be changed to 0.0018 if the steel was 420 megapascal. So afterwards, we have to design this. So simply, depending on the case and the end condition, we calculate 3 different factors for one direction. So for example, we are designing for x direction. We have to know Cx dead load Cx live load, and Cx negative. These three factors we have to know. So if our case was 4, fourth one was our case. So our M value was, suppose it was 9. It is Lx or Ly ratio. Just round it off to nearest value. No need to interpolate. So for 0.9 M is equal to 0.9, and the case is 4. The Cx, this table is for, oh, sorry, this is for British coefficients. You have to use the ACI table one. This one is ACI. So this is one for dead loads and ACI. So 0.9 and case 4. We can get Cx dead load as 0.041. Okay, is equal to 0.041. Similarly, Cx live load would be in the second table. This one is the live load coefficients, and 0.9 and case 4 we can get is as 0.049. 0.049. And for the negative moments, case 4 and 0.9 we can get as 0.054. 0.054. This is Cx, dead load, live load, and negative. We have to multiply this dead load by 1.2 QD, get factored dead load. We multiply this 1.6 QL factored live load, and this is similarly factored load. And into Lx square, because it is x direction, Lx square, Lx is. Remember that x direction does not mean x like this. It means shorter direction. It can be, x can be like this also, depending on shorter direction. X direction is always shorter. So this would give us dead load moment, this would give us live load moment, and this would give us negative moments. Negative. The top two would give us that positive moment, and the bottom one would give us negative moment. The total positive moment would be M plus dead load and M plus live load. Simply we can add them, and the next moment is. So after getting the moments, this procedure is different for moments. Afterwards, it's exactly the same as D. That if we have gotten the moments, we can find steel area by R is equal to mu over BD square, and we can use rho is equal to omega 1 minus under root 1 minus 0.14 R over FC dash, and we get omega 0.85 FC dash over Fy. Just simply we have to plug in the values and we can calculate positive field from M positive, this one negative field from M negative. We have to do this in x direction, and we have to repeat the same procedure in y direction. Just this coefficient will be different. We have to use y coefficient in that case. We have to use, for example, this was negative moments. So for the same M, for the same case, we have to just check the Cy value. We have to use the negative coefficients. We have to change the coefficients, and we have to change this Lx direction, Lx length. We have to use Ly in that case. The load will remain the same. So after designing in both direction, Lx and Ly, y direction, so we have to just use C dead load, Cy live load, Cy negative, and this would be Ly square, Ly square, Ly square. This is only the difference in x and y direction. And yes, when we were using this, R is equal to M over BD square. So in x direction, we would use D short. This one. This. You use this D short in x direction. And this D long we would use in y direction. This would be also here in M over BD square, using D long. Okay, so this one would be different in calculating moments, calculating the steel. So after we have got the steel, we can easily check what is required. For example, the manual. So this is the steel table. So if we have got steel as 500 millimeters square, 500 millimeters square, so we can simply check that for slab is provided usually for main bars or for short direction, and number 10 is provided for longer direction. So we can easily check for 500 millimeter what would be our spacing. So this is 516. Spacing would be 50 millimeter center to center. One moment. Okay, sorry. So just memorize this file. It can be asked in quiz. So after we have got the steel, we have to show the reinforcement detailing of the slab. So for reinforcement detailing, we have to show it something like this. That if this is our slab, example, this is our slab. For example, I'm cutting a slab like this. So this is suppose our shorter direction Lx. This is our longer direction L1. So it would be like this from end to end. The second bar would be curtailed at some distance. This distance. So this distance is simply L by 8. This one is L by 8. So this is Lx. So we'll use the distance as Lx by 8. Okay, so curtailment length would be parallel to the distance. What is the total length of the slab in that direction? So we'll curtail it according to that. So this would be our main steel. That one bar we would provide fully, and the second bar we would curtail at some distance. This is our main steel. Other steel would be like this. We can provide it one bar this, and we are curtailing the alternate parts in both direction. In this direction. So this one and this one, we are curtailing it at Ly by 8, Ly by 8. So we are curtailing both bars. Remember, these are bottom steel. Both of them are bottom steel in X and Y direction. Bottom meaning positive steel, X and Y direction. We have to draw this diagram like this. This is a steel diagram. Something like this. We can curtail alternate bars in each direction, or we can provide a full bar and a curtailed bar. It is up to us. But usually in main direction or the shorter direction, we provide one full bar and the second bar we curtail. In the longer direction, we curtail bars in opposite direction alternatively. And again, for the negative steel, so this is negative means top steel and it is negative. So we show negative steel by dotted line. So that positive, sorry, the negative steel in X direction would be shown. For example, this is another slab. So this is negative steel in X direction. We are only providing steel at the support. You can say this length as L by 3 and this L by 4. And since this is Lx, so Lx by 3 parallel to the length. The other bar would place alternatively. That means that this would be like this. It would have L by 4 here and Lx by 3 here. So we are placing bars alternatively. That in one direction, if it is 4, then in the second direction, that would be more. Okay, this is how we place in. If there are two, if it is an internal support, if this is an external support, for example, this. So we simply curtail it at Lx by 5 length. At Lx by 5. So these lengths are given. You have to memorize them. The support is at Lx by 5, while the internal are alternative. First is L by 4, the second part is L by 3. And similarly in the y direction, exactly the same. Just the length you'll be using at Ly. Here we were using Lx, in that direction would be Ly. So this is how we show the top steel. And if this is a curved portion like this, we will be placing steel like this, top steel like this. The length would be same, Ln by 4 here, then Ln by 3 here. And we can use any of Ln. We can use Ln here because this is in the middle of Lx and Ly, so we can use Ln here. Ln is the clear span. All right, so this is how we are going to show the curtailment. This is for curtailment. For bent up, it's almost the same. Just the difference is, for example, this is a slab. This is another slab. So for bent up bars, simply we provide one bar fully throughout the length. The second bar we would provide at some distance, then we would bend it up and move it to the other slab. So this bent up bar here, we can bend up at this Lx by 4 distance. This is Lx, then the distance would be Lx by 4. So we can bend it at Lx by 4 distance, and we can extend it into the other portion as a negative steel for the other slab. So bent up saves our steel because one bar is going as positive in the bottom, then it changes into negative for the same slab, and again negative steel for the other slab. So this is saving our steel, but it is difficult to provide in actual conditions because we have to bend all the bars. So you can see the distance is here, that we are extending the bar at L by 3 distances, and these distances are L by 4 and L by 7. The bent up distances. If the bent up bar is if the bar is being bent up over internal support, the distance we would use as L by 4. If it is bent up at external support, the distance we would be using as L by 7. Just we have to memorize this. The same thing is done for y direction. The coefficient are same, just the bar placement is in the y direction. So this is how we can provide bent up and curtailment bars. The last thing is torsion steel. So for example, this is a corner slab. This one is a corner slab. In the corner slab, some twisting or torsion would be produced. So to stop them, something crack will produce like this. This would be our top cracks, and these green cracks would be our bottom cracks. So to stop these cracks, we will provide a steel in the other direction. So these are our cracks, crack formation. The steel would be provided to stop these cracks. So green cracks are bottom and the red cracks are top. So to stop the bottom cracks, we provide steel, bottom steel like this. This blue is bottom. And the top steel is dotted steel, so I'm showing it as red. So the top steel would stop the top cracks and the bottom steel would stop the bottom cracks. So this is how we can stop torsion. And other way is to provide simply a mesh. The mesh is simply a bottom mesh and a top mesh, two meshes actually at the bottom and top, and the distance of mesh would be L by 5. Whatever the length is at in this direction, for example, this was Lx and this was Ly, will be Ly by 5. Okay, this is how we have to detail the slab. It can be asked. I think it was asked in some previous paper that we have to show the slab reinforcement detail. And yes, we have to sketch the reinforcement detail for it also. The slab. So we must. This was all for residential building. Yeah, this is all for residential building. The second portion is for commercial building, so it is small one, but we haven't done. Okay. So they are saying that extract 2D frame from 3D building. 2D frame grid 1. So for example, this is our grid 1. We have to extract 2D frame. So 2D frame at grid 1 would be this. Is that understandable? That this whole line is grid 1. So at grid 1, what would be our frame? So this is our frame. That, for example, this was in 4. Yes, ABCD 4. So we have 4 points and 1, 2, 3, and 4 beams. So this is like this. So this is grid at 1. We have extracted grid 1. Deformed shape due to vertical and lateral loads separately. So our deformed shape would be something like this. Like this. We will have some deformed shape like this. So you can get an idea from this from just simply drawing 2D frame like this in any software, and we can check how our frame is going to be deflecting under the gravity loads. So this is under gravity loads. We have to just check this, verify this for gravity loads. For the second part is for wind, for earthquake loads. For example, if this was a frame, earthquake load always acts at the base, and it displaces our building in lateral direction. So our building would be displaced it like this, something like this. So this is our displacement or story drift. So our building earthquake would displace our building like this, in this like this. So this was asked in the first part that we have to show the reform say due to vertical and lateral loading. So lateral loading is earthquake loading. And we have to also show the variation of earthquake and wind load. So for example, if this was a building, the earthquake load, we know it acts at base always, that we acts at base. The maximum direction would be generated at base. As it moves to the top, the forces in each story are reduced. So our earthquake loading would be something like this. This is our earthquake loading. That we have maximum force effects at the bottom, and as we move to the top, the force is reduced in each story. But in the case of wind, it's the opposite. For example, the wind is stronger as we move upwards. So for example, at top story, much higher value of wind is acting, but at ground level, very low or negligible wind is acting. So this is for wind loading, and this is for earthquake loading. Although both are lateral loads, but the loading pattern is totally different. So we have shown the variation of earthquake and wind load for this frame. Second is critical displacement. Okay. So for example, this is our column and this is our beam. We can define the longitudinal axis of our column as 1. This is normal convention that we define the longitudinal axis of our column or the longitudinal axis of our beam as 1. So this is always one axis. The two axes would be perpendicular to one axis. So this is two axis. This is two axis. The two axis is perpendicular to the longitudinal axis. The third axis would be out of plane. So for example, this is our third axis. This is our out of plane axis. This is our third axis. This is our out of plane axis. So for beam, we know that the critical forces are bending moment and shear force. Shear force and bending moment. These are critical forces for a beam. So the critical forces for beam would be like V22 because this V is in the direction of second axis. So the critical force would be V22. And the bending moment is in the is about third axis. So we can write as M33. So these are the critical forces for beam. V22 means shear along 22 axis, and M33 means moment about 33 axis. So these are critical forces for beam. In case of columns, uh, axial load is also acting, and this axial load due to some eccentricity can generate moment about both 2 axis and 3 axis. So our critical forces for column would be uh, F11. This is the axial load along the 11 axis. M22 movement about 22 axis and M33 movement about 33 axis. So these are all critical forces for beam and column. This is for gravity loading. These are for gravity loading. In case of earthquake, a little bit different would be they would be a little bit different. Fine. So these are critical forces this is for gravity loading. For suppose earthquake loading, this is again our column. This is again our beam. So earthquake load X horizontally. Earthquake load. So what would be our? This is again 1. This is again 2. This is again 3. So the critical force would be for earthquake for column, that would be V22, because this shear would be generated due to earthquake, so it would be resisted by V22. Again, some gravity load is also acting, so V22, and this was F1 or F11, and this gravity load would generate moment about 1 axis also. So we'll write moment as 1 and moment as M22. This gravity load is generating moment about 1 axis. This is rotating the column in this direction also. This is about 1 axis. So twisting the column is actually. So this twist is actually torsion, and this is M11. This is torsion. Okay, so this was earthquake loading on column. In beam, due to earthquake loading, for example, like this, so axial force would be generated. That this is axis 1, this is axis 2, and this is axis 3. So axial force will be generated, that will be like F11. Again, V22 and M33 would be present, and this axial force would generate some torsion, again M11. This torsion would again be generated. So these were critical forces. So the question is, we have to find the critical displacement at joint 15. So joint T15 is this one. This one. So in the frame, this is our frame. So this is joint E15. So we have to find the critical displacement. So if earthquake load is acting, they are saying that earthquake load is acting. So what would be critical forces here? That would be, this is, suppose this is a column. This joint is a column. So the critical force would be like F. We can actually use these axes also. They are saying that axis, okay, if we are using the local axis, we have to actually use global axis here. Global axes are this: X direction, Y direction, and Z direction. Because this is a joint, so we are checking the displacement of joints, so we have to actually use the global axis here. Those 1 to 3 were local axes of each column and beam. So for joint, we have to use the global axis. So actually, this axis is X axis. In this direction, it was Y axis, and in upward direction, it is Z axis. So this earthquake load in X direction, this would generate a reaction in right as R in X direction. This earthquake load in X direction is generated a reaction in X direction again. Again, we have due to gravity load, we have our RZ direction, that in this direction we have some load, that is RZ, and again we have moment about Y direction, My. This Rx load is generating moment about Y direction, so we have My. So these are the critical forces for this joint 15. And again, of course, we have some torsion also, so we can write it as Mz also. but it is a minor. This is minor because this is torsion. We can just write as mg and torsion. So these are critical forces for this joint RZ. If we have to write critical displacement as it is asked in question, then simply Rx would produce delta x, RZ would produce delta z, My would produce theta y equation, and Mg would produce theta z. Simply we can write, if we know the critical forces at some point, we can simply convert them into the displacements and rotations. Okay, so this is how we are going to write the critical displacement. The critical force in column C1 that we have already discussed, that critical forces would be in column. Due to gravity loading, these three forces, due to earthly loading, these four forces. And remember M11 is torsion at and you can mention it as this is torsion, so it is going to be a minor force. It would be present, but it would be a minor force. But we have to mention this. We cannot skip this. So we can show this local axis. Yes, we have to show these according to local axis. So like F11, M11, something. The last question is list down the parameters needed to apply auto-seismic loading. So for SAP, like before we discussed, so for SAP, we require some factors. So we have to memorize these factors. First, the formula is time period is equal to CT H n. Hn is the total height of the building raised to the power x. So first we require CT. Second parameter we require x. These parameters are required. Building height would be automatically calculated by SAP. The second thing we require is SS and S1. These parameters would be, these parameters are, I think, ground. Yes, these are ground accelerations. These are ground acceleration factors, and these actually show the acceleration of ground in terms of g. G is the gravity acceleration. So these factors would depend upon the location where we are uh, actually constructing the building. So the ground acceleration at that point, the we can calculate this from latitude and longitude of our location. So these are SS and F1, and afterwards we have FA and FV, and these FA and FV are actually soil parameters that we can get it from soil, that whatever the class of soil is A, B, C, D, E, U. So we can check the soil class, and from tables we can get the values of FA and FV. Third thing is SMS and SM1. SMS and SM1. So these are actually products of SS into FA and S1 into FV. Simply multiply them, so we'll get SMS and SM1. So after we have SMS and FM1, we can calculate SDS and SD1. We have to memorize this. So SDS is 2 by 3rd of SMS and SD1 is 2 by 3rd of SM1. So these factors would be required. And apart from this, 4 factors are also required. That does, I think it was R omega C D and I. Yes, these 4 factors R omega C D and I. So this is depending upon R is depending upon building type. Omega overstrength factor, I is the sorry importance factor, and CD is something. So we can get these factors from tables. We can directly get these factors from tables. So this is the procedure, and if we open ETABS, we can check. So if we go to defined and load patterns, If we define a seismic load pattern, seismic, just change its name. And ASCE according to ASCE, add new little load, modified little load. So if we check this, they are requiring CT and X. The first factor we have written CT and X. So CT and X are required. Then the story and this also uh, that's explanatory. So SA and SS, SA and S1, sorry. So SA and S1. So these are required. Sorry, this is SS and S1. So yes, SS and S1. So these are required. This is depending upon our location, and FA and FV. They are it is automatically calculating from soil type. So either we can specify the soil type, it can automatically calculate the FA and FE factors, or we can specify FA and FE values. So after uh, SMS and SM1, simply multiplication. So if we see this FV and SS, FV and S1, these are SMS and SM1. So we are multiplying this by 2 by 3rd, and we can get STF and SD1. So it is again automatically calculating these values. So SDS and SD1. The four other factors are R, omega, CD, and I. So we have to specify this. R is response, the building type, overstrength factor, CD is deflection, amplification. Yes, CD depends on damping of the building. So and I is omega. Oh, sorry, importance factor. So you can get these factors from tables. Simply, we have to mention their names only in this, and we have to only list down these patterns. So this was all about multi-story building. That we have to know how to extract the frame. We have to check what are the critical forces on the frame, and we have to know where the column or beam would be deflecting and what would finally the how we have to apply seismic load. But manually, this was manual calculations, and in ETAB again also. Right, any
Brother,
issue in this? Yes.
in here that equation T is equal to CT into HM. That what is T?
Time period. The time
Okay.
period of our building, like we have done in structure engineering, I think. We calculate time period of our building.
Okay. And what is the X?
Yes. Sorry. TT.
What is the X? No, no, no. What is
X
X
is
on same thing?
X is just power. You can get it from tables. This CT and X, these are directly we can get from table. This random building. Actually, we use 3 by 4 in UBC. UBC we always use 3 by 4. We raised HN to 3 by 4 power. But in IBC, this latest one, they have changed this power depending upon building type and building stories. Its height. So it's actually dependent upon the building height and type.
Okay, brother.
Any other? So just go through these past papers, all of them, try to solve them. I think this is a smaller part. The steel one is larger. Also, there are three slides of the membrane. That is almost all is theoretical. So you have to also go through that part also.
Okay, it means from that part also questions may become.
Yes, theoretical questions.
Okay.
It's all theory. That what are rich components and is deck slab and how we have to provide deck slab, what is reloading and all that. Like we have done in again structural engineering in the lab portion of Sarali. So almost the slides are similar to those. Almost all. There are some differences. Any other issue?
Brother, if you have solved examples, I mean past papers, please share the solution.
Past papers I haven't solved yet, but I inshallah solve it by tonight. Inshallah. So I'll send it them.